Our final lesson in this unit and our final lesson in our investigation of nuclear physics is, of course, about fission and fusion. And these are two very special types of reactions that involve the nucleus of atoms. And basically, these are the interesting procedures that fuel both atomic weapons and power generation in Ontario and really in the rest of the world as well. So we're going to take a look at some of these things today, and we're going to kind of go from here. So basically what's involved, we're going to look at fission first, and then from fission, then we'll turn our attention to fusion a little bit later. So this is one type of nuclear reaction. And here we have some really big, heavy nucleus, and it splits apart into two smaller nuclei. Okay? What we're going to investigate primarily is what we see in the CANDU reactor, which is a Canadian nuclear reactor that we see locally here in Southern Ontario. And it also there's also other locations where we see the CANDU reactor, but it uses uranium and enriched uranium, so one special type of uranium called uranium-235. And what ends up happening is that this is a very unstable nucleus. And we know that it would normally decay just by itself using alpha decay because it is unstable. But what we do is we take this unstable nuclei and we bombard it with an extra neutron, so it becomes even more unstable. And eventually what happens is that this thing gets so energetically unable to stay together that it spontaneously splits then into a couple of different particles, barium and krypton. And what we get is we get these two what we call daughter nuclei, and we get a couple extra neutrons. So we put one neutron in, we get two neutrons out, and then we get this massive amount of energy. Okay? And so really, this is what happens in a CANDU reactor. There's a couple really great YouTube videos from Ontario Power Generation where it will show you how a power plant using the CANDU reactor works to generate electricity. It's interesting. You should definitely take a look and see kind of how they operate. So let's talk about, basically in this example, the one that we've just talked about, the two nuclei that are produced, we kind of mentioned they're called daughter nuclei, right? In this case, they're barium and they're krypton. In other power generating stations or in other nuclear reactions where we're not using uranium-235, you would get different daughter nuclei. But in this case, we get barium and we get krypton. And one of the most important products in this fission reaction are the two ejected neutrons. So we put one neutron in, we get two neutrons out. So in a reactor, those two neutrons are controlled, right, by a product called moderation. So they're slowed down, they're captured, and then they're used again. And proper moderation leads to this massive chain reaction, right? So when we take a look at this, this is what we get. We get basically barium, and we get krypton, okay? And we get these really, really, really important neutrons. So we put one neutron in over here, and what we end up with is we end up with two neutrons over here. So that's in one fission reaction. And then in another fission reaction, of course, two neutrons becomes four neutrons. So basically here's the equation again. Let's take a look. So in our first step, in our first fission reaction, we get, at the end, we've got two neutrons. Well, then these are captured, moderated, and used again. So now these two neutrons then both bombard another two uranium nuclei. And so then at the end, we've got four neutrons. After the third reaction, those four neutrons have now become 8 neutrons. After the fifth, we've got 32, and so on and so forth until, you know, we're kind of at a point where we've gone from 2 to the power 1, 2 to the power of 2, this is of course 2 to the power of 3, and 2 to the power of 5. Well now, let's say after the 10th reaction, we've got 1,024 neutrons. After the 20th reaction, we got more than 1,000,000 neutrons. And this is what's called a chain reaction, right? And this whole entire process, right, within 20 steps in this kind of a chain reaction, we got more than 1,000,000 neutrons that are produced. And so if each step takes about 10 nanoseconds, to get this many neutrons is less than a microsecond, right? And so what can happen if you don't moderate very carefully, you can get kind of a runaway chain reaction. And that runaway or uncontrolled chain reaction is what happens in atomic bombs, right? So in general, reactors control a chain reaction, but uncontrolled chain reactions happen in atomic bombs, and especially you know, these especially like the two that we saw very famously that ended World War II. And of course, we've seen other examples of these things all the time in movies and on the news. And they really show you just how much energy can be released in one of these uncontrolled chain reactions. Okay, so basically, we want to talk about how much energy can be released in a fission reaction. And the answer, of course, is related to, okay, well, how much energy can one nucleus give off? And for that, we have to turn to this concept known as binding energy. And it's basically a measure of the strength of kind of that nuclear force between the different parts that make up a nucleus. So between protons and neutrons, when we split those apart and we get more stable, you know, that energy has to go somewhere, and of course it goes to us. So we're going to look at the quantity of energy per mole, all right? Because really, if you look at per particle, it's a teeny, teeny, tiny bit of energy. But if you look at per mole, then we're up to something that, you know, we can visualize. So when I go from fission, I'm starting with a really big nucleus, and I'm creating two much smaller nuclei. And this difference in energy, the difference in the binding energy between here and here and here, is about 100 gigajoules per mole. So when you think about joules, you know, this is 100 gigajoules of energy in 1 mole of substance. And that's basically the approximate amount of energy that's released in one fission reaction. So we're talking about massive quantities of energy, okay? So this is fission here, and we're going to come back to this graph, and we're going to look at fusion, which is over here, in a moment, okay? So if fission is taking something big and splitting it apart, you may have guessed that fusion is taking something that is very small and binding it together. And of course, this right here is a very typical fusion reaction where we have tritium, which is one isotope of hydrogen, and deuterium, which is another isotope of hydrogen, and we fuse them together to create helium and a neutron. Okay, so this is very typical of what we see in the sun. Okay, and here is the fusion reaction where we have deuterium and tritium, and we're fusing them to create helium, a neutron, and large amounts of energy. Okay, so again, we can look at this binding energy, and really we're going to look at this section of the we're going to look at this section of the graph now, and really we're going to go from kind of binding energies down here to a binding energy up here. This is almost 4 times as much as what we get from fission. This is about 400 gigajoules per mole. So that's about 4 times as much energy as fission. And this is why fusion reactors have been something that's very, very sought after, right? So this is basically how our sun produces energy, right? It involves a number of complicated cycles of nuclear reactions. One of the main reasons that we don't use fusion all over the place, because, you know, you might say, if it creates 4 times as much energy as fission, then how come we don't use that in power plants? And one of the reasons is because right now, it's just not as efficient. And so we end up putting almost as much energy in, or sometimes even more energy in than we get out to power a fusion reaction. So that's one of the reasons why we don't see it very often. But this is kind of a general overarching look at fission and fusion reactions. I would definitely say go and take a look on YouTube. All you need to do is type in a couple of these things. There's some really, really good little videos and demonstrations that will show you kind of graphically how these things work and how they all fit together. All right, enjoy, and that's the end of this unit.